Good morning students, welcome to the class. Today let us study about the homomorphism. So this is the 15th session on groups. First let us study about the homomorphism. A mapping F from a group G, star or dot into a group G dash, star is said to be homomorphism if for all A, B belongs to G, f of A dot B is equals to f of A dot or star. Whatever the binary operation we use, we can take that one here. If it is a dot, then it is dot, or if it is a star, then it is a star. So f of A star B is equals to f of A star f of B. So take one more definition, isomorphism. A mapping F from G to G dash is said to be isomorphism if first point F is homomorphism, second point F is 1 1 and third point F is onto. If it satisfies these 3 points, then we can call it as an isomorphism. That is, first it should be homomorphism, after that it should be 1 1 and onto also. If there exists an isomorphism from group G into G dash, then we say that G is isomorphic to G dash and vice versa, and G dash is isomorphic to G, and we write it as G is isomorphic to G dash. So this is G bar, this is the symbol of isomorphism. Take one more definition, endomorphism. A homomorphism F from G to G dash, from G to itself, from a group G into itself is called endomorphism. So instead of taking another group, we can take here the same group G to G only, then we can call it as an endomorphism. Next one is automorphism. An endomorphism F from G to G itself is to be automorphism. Here also first it is endomorphism, means it is a homomorphism from a group G into G dash. Then its mapping F from G to G is called automorphism if it satisfies these two conditions. If it is 1 1 and onto, then we can call it as an automorphism. Take one note. If F is 1 1 and onto, then it is called bijective function. This we know. If a function satisfies both 1 1 and onto, then we can call it as an onto function. Let us take one more definition, zero or trivial homomorphism. So a homomorphism which maps every element into the identity element is called the zero or trivial homomorphism. So that is, first it should be a homomorphism of every element into the identity element. It maps only to the identity element, then we can call it as a zero or trivial homomorphism. Take some properties of homomorphism. Take one theorem. If F is a homomorphism of G into G dash, then F of E, first point, F of E is equals to E bar, where E and E bar are identity element of G and G bar. And second point, F of X inverse is equals to F of X whole inverse for all X belongs to G. Take proof. First one, for all X belongs to G, we know X is equals to X into E because E is the entity element, where E is the entity of G. Then this implies f of x is equals to f of xe. This implies f of x is equals to f of xe. From the definition of homomorphism, we know, from the definition of homomorphism, just we have seen here, this is the definition of homomorphism. This is f of A star B is equals to f of A star f of B. So we can remove star also. It is simply f of AB is equals to f of A into f of B, and vice versa, f of A into f of B is equals to f of AB. So here f of x into E is equals to f of x into f of E. Take this one as equation number 1. Let E bar be the identity of G bar, and we know that here for all x belongs to G, f of x belongs to G bar, because we know this one here. All elements x belongs to G and their images f of x belongs to G bar. This implies here multiplying on both sides with here entitlement, f of x into E bar is equals to f of x, because E bar is the entity element. That is, f of x is equals to f of x into E bar. Take this one as equation number 2. So from equations 1 and 2 we have here. Here we have equation f of x. F of x is equals to f of x into f of e. And in second equation we have f of x equals to f of x into e bar. RHS we can equate here because LHS are equal. So this implies here f of x into f of e is equals to f of x into e bar. This is equation 1 and this is equation 2. RHS of equations 1 and 2. This implies here we can cancel f of x on both sides by left cancellation law. It is simply f of e is equals to e bar. So for all x belongs, this is the proof of a first result here. So f of e is equals to e bar we got. Let us prove second one. So second one is for all x belongs to G. This implies here x inverse is also belongs to G because G is a group. Every element has its inverse. So this implies here x into x inverse is also belongs to G because by closure law it satisfies closure law. So you know closure law means for all A, B belongs to G, A star B is also belongs to G. This star may be into or simply it is dot or simply we can write directly A into B also. So x into x inverse belongs to G. So now let us take the function here f of x inverse is equals to again by the definition of homomorphism, this is f of x into f of x inverse. Take this one as equation number 3. And also we have here x into x inverse is equals to e because x and x inverse are reciprocals to each other. That is inverse is equals to e. This implies here f of x into x inverse is equals to f of e. It is equals to from equation 1 from this first result we have proved here f of e is equals to e bar. This is here. Take this one as equation number, this one as equation number 4. So from equations 3 and 4, again here from equations 3 and 4, LHS of equation 3 and 4 are same, so we can equate their RHS. F of x into f of x inverse is equals to here e bar. RHS of equation 3 is equals to RHS of equation 4. So this implies the inverse of f of x is f x inverse because you know if the product is E means they are reciprocals to each other. We know this because here A into A inverse is equals to E means then this implies here A inverse is the inverse of E. So this implies f of x is the inverse of f of x is f of x inverse. So this implies here f of x whole inverse is equals to f of x inverse means these two are reciprocals to each other. This implies here f of x whole inverse is equals to f of x inverse. This is the second result. Take one more theorem. If a mapping f from G to G bar is a homomorphism, then the range of f, that is f of G, is equals to f of A, such that for all A belongs to G is subgroup of G dash or G bar it is. Since f of A belongs to G bar, for all A belongs to G, this implies here f of G is contained. Belongs means it is a subset or it is contained in G bar. Now let us take 2 elements of this G bar. Let x bar, y bar belongs to f of G. Be arbitrary. Now to show that f of G is subgroup, that is we have to establish here the necessary and sufficient condition of a subgroup is for all A, B belongs to G, AB inverse is also belongs to G. That is here x bar, this we know here for all AB belongs to H, subgroup definition here. AB inverse is also belongs to H. This is the necessary and sufficient condition for a subgroup. So here for all x bar, y bar belongs to f of G, you have to prove that here x bar, y bar inverse is also belongs to f of G. Now clearly by the definition of f of G. So we have here x bar is equals to f of x and y bar is equals to f of y because here x bar and y bar belongs to f of G means the elements are in this form only f of x and f of y for some x y here. Now consider, we have to prove this one, no? You have to consider this one only, x bar y bar whole inverse is equals to x bar is f of x and y bar is f of y and its inverse. Now f of x into f of y inverse, this is by previous theorem, just we have proved here. So we know here the inverse of f of, just in previous theorem, in theorem number 37 we have proved here f of x whole inverse is equals to f of x inverse. Just now we proved, we use the same result here. So f of y whole inverse is equals to f of y inverse. This is equals to, again you apply the definition of homomorphism. So f of x into f of y inverse is equals to f of x into y inverse. So that is here, that is x bar y bar whole inverse is the image of x y inverse under f. So here it is, f of means it is the image of f here. Since x y inverse belongs to G, then this implies f of x y inverse is also belongs to f of G, because here x and y are the elements of G, means f of x y inverse is also belongs to f of G. And this implies here x bar y bar inverse belongs to f of G for all x bar y bar belongs to f of G. Hence f of G is a subgroup of G. So this is the necessary condition of a subgroup. If x bar y bar belongs to f of G, then x bar y bar inverse is also belongs to f of G. This is enough to show that this is a subgroup. Take one more theorem. Let f from G to G bar be a homomorphism and H be a subgroup of G, then f of H is again a subgroup of G bar. Now we have f of H is equals to f of H for all H belongs to H. Since for all H belongs to H, comma H belongs to G, and this implies here f of H belongs to G bar. This implies here f of H is contained in G bar because f of H belongs to f of H here. F of small h belongs to f of H. Let us take two elements here. Let x bar comma y bar belongs to f of H be arbitrary. Now to show that here f of H is subgroup of G bar. Again we know here. So this is the necessary and sufficient condition of a subgroup. Then x bar y bar inverse also belongs to f of H. Let us take two elements here. X bar as f of H1 and y bar as f of H2. Then consider x bar y bar inverse is equals to f of x is H, f of H1 and f of H2 whole bar. Again just we have done in previous case. So it is f of H1 as it is, and by previous theorem, theorem number 37. So we know that here f of H, this we know here, theorem number 37 is f of x whole inverse is equals to f of x inverse. So this we know. So according to this it is f of H2 whole inverse is nothing but here f of H2 inverse. Again apply the definition of homomorphism. So homomorphism is what here? F of A into f of B is equals to f of AB. So it is f of H1 into H2 inverse. Since H1 and H2 belongs to H, then this implies here H1 into H2 inverse is also belongs to H. This implies f of H1 H2 inverse is belongs to f of H. So this implies here what here? X bar y bar inverse belongs to f of H. For all x bar y bar belongs to f of H. Hence f of H is a subgroup of G bar, and we know here this is again the necessary and sufficient condition to prove that it is a subgroup. Take one more theorem. Let f from G to G be a homomorphism from group G into itself, and H is a cyclic subgroup of G, then f of H is again a cyclic subgroup of G. So what you have to prove is here, first you have to take f as a homomorphism and H is a cyclic group. Then you have to prove that here f of H is again a cyclic group. Like this you have to prove here. Let f of H is equals to f of H for all H belongs to H. Now clearly f of H is a subgroup of G. Because here H is a subgroup means f of H is also subgroup of G. By data, H is a cyclic subgroup of G. It is given here. Means it is generated by some element. Let A belongs to G, be a generator, that is H is a cyclic group generated by A. This we know definition of cyclic group generated by A means the elements in this form are in the form of A square, A cube, etc. So generated by A means it is in this form here. Now to show that f of H is cyclic, let us take here x belongs to f of H, be arbitrary. Then there exists y belongs to H such that f of y is equals to x. Since y belongs to H, then this implies here y is equals to a raised to m. Why it is y equals to a raised to m means H is a cyclic group generated by A means the elements of H are in the form of A square, A cube, etc. So it is equals to A raised to m for some integer m here. So let us take here, let x is equals to here f of y, this is equals to f of A raised to m, where when m is a positive integer, let us see what happens. When m is positive integer, here x is equals to f of A raised to m. A raised to m means f of a into a up to m times it is. This is equals to, x is equals to, apply this definition of homomorphism. So again the definition of homomorphism is what? Homomorphism is f of a into b is equals to f of a into f of b, no? So for that it is f of a into a means you have to take m times it is. This is f of a up to m times. This implies here x is equals to f of a, here we have how many times? M times. So it is f of a whole raised to m for all x belongs to f of h. So because here f of a generates the subgroup of f of h, because here it is in the form of f of a raised to m means it is the generator here. This implies here f of h is equals to cyclic group generated by f of a. Here the elements are in the form of f of a only, is cyclic. So now take one more case, when m is negative integer. Let m is equals to minus k, where k is positive integer again. Now equation 1 implies here, equation 1 is x is equals to f of a raised to m. Then this implies here f of a raised to m is minus k, a to the power of minus k. So this a to the power of minus k can be taken as here a inverse to the power of k. So it is again f of a inverse to the power of k it is. F of a inverse is k times it is. A inverse into a inverse up to k times it is. So let us again apply here, apply the definition of homomorphism. Here we don't have any bracket here. Apply the definition of homomorphism. So it is f of we know here f of a into b is equals to f of a into f of b. Here we have k times f of a inverse, no? It is f of a inverse into f of a inverse into f of a inverse up to k times. So f of a inverse into f of a inverse k times we have, no? It is f of a inverse whole raised to k it is. So this implies again, we can take this one as here, this is again by previous theorem here, by theorem number 37, f of x inverse is equals to f of x whole inverse, no? So it is f of a whole inverse to the power of k. So it is, we can multiply these two, no? F of a to the power of minus k. So that is here x is equals to f of a. Here we know minus k is nothing but here we have taken here minus k is equals to m. So it is equals to here what? F of a to the power of m for all x belongs to f of h. This implies what here? This implies here x belongs to f of h. So this implies here f of h is equals to f of x is equals to here f of a to the power of m means it is a cyclic group generated by f of a. This is a cyclic group generated by f of a, is a cyclic group, is cyclic subgroup of G. So this is the proof of this theorem. That is here, if the statement here is what? The statement here is if f is a homomorphism and G and H is a cyclic group of G, then f of H is again a cyclic group of G. So here this we proved this one here. So here we proved f of H is again a H is cyclic. So lastly we proved here f of H is also a cyclic subgroup of G generated by f of a. So this is the proof of this theorem. So if you have any doubts or any this one you can ask here.